Okay, let's start out by talking about parabolas. Okay, if you don't know what those are, you'll soon find out. Okay, let's start out with something you're familiar with here. Okay, let's talk about polynomials first. Okay, you should have learned about these in previous classes. Let's go ahead and reiterate what you learned previously. Okay, a polynomial in the variable or unknown x is an algebraic expression of this form. Okay, a sub n, x to the n, plus a subscript n minus 1 times x to the n minus 1, plus so on and so forth, all the way down to a sub 1x plus a sub 0, or what sometimes we call a naught. Okay? Alrighty. Let me mention a couple things here. All the exponents on x here, so n minus 1, all the way down, have to be non-negative integers. Okay, they have to be non-negative integers. Okay, remember non-negative integers would be what? 0, 1, 2, 3, 4. Okay, that would mean whole numbers, essentially. Okay, remember whole numbers include 0. Okay, alrighty. These a's here, a subscript n minus 1 and so forth, or a subscript n, which I usually just read as a sub n, a sub n, a sub n minus 1, and so forth. These are actually what? Numbers being multiplied on those powers of x's. Those are usually called coefficients. Okay? So these are the coefficients of those various terms. Okay? So those are coefficients, numbers being multiplied on those powers of x here. Okay? So those are coefficients. And notice the way we've set up this scheme, we've got what? The subscript on the a corresponds precisely to the power on x for that particular term. Okay? All right. So that looks like a good way to do it here. Let me throw this in here. I've got x squared plus 3x plus 1. That's a polynomial here. Okay, you can see this. Excuse me. That's a polynomial. Okay. What is the coefficient on x squared? Well, I really wrote it in there for you. The coefficient on x squared is actually implicit. That means it's not written explicitly. It's actually a 1. Okay? If you were to force it on there, it's actually a 1. The reason why we usually drop it is computationally it's useless, right? Multiplying by something by 1 leaves that something unchanged, so there's really no point in even doing it. So we usually just leave that off there. Okay, but it could be done here. Okay, we would say then in the parlance of what we have right above here that a subscript 2 is equal to 1, a subscript 1, or a sub 1, is 3, and a sub 0, or what I like to call a naught, is actually equal to 1. This is a polynomial. 13 is a polynomial. Yep, just a constant number there is a polynomial here. What that would simply mean is all the previous terms don't appear at all, right? And you're just left with a constant term. Okay? Let's take a couple examples of expressions that are not polynomials here. I've got 7x plus 1 plus 3 times x to the minus 1 power. This is not a polynomial because notice that the power on x in this particular term is in fact a negative number. And remember, our exponents to be on a polynomials had to be what? They had to be non-negative integers. Well, negative 1 is not a non-negative integer. Okay, here's another expression I threw in when I was going through this. How about the square root of x? There's another good example. That's not a polynomial because the square root of x actually corresponds to what? X to the 1/2 power. Okay, 1/2 is certainly not an integer, right? Okay, so it is not a polynomial there. Okay, now we often give names to such expressions, forming what we will call polynomial functions. Now we'll talk about functions in greater depth here. Again, you've probably heard of those before. We're going to talk about those in chapter 3 as well, so the next chapter in great depth here, functions, but we'll have a slight introduction here in this chapter and in this video. Okay, let's just give names to the polynomials. Think of it this way. I'll say f of x, that's how it's read. It's not like multiplying. That's f of x equals 3x plus 1. You can see that's a polynomial. Okay, g of x is x squared minus 1. You can see the 3x plus 1 and the x squared minus 1 are both polynomials. So we would say f and g are polynomial functions. Now the thing about the functions here is we can do an evaluation. Okay, so we would read like this, f of 2. Okay, what I'm simply doing is letting I'm assigning the value 2 to x here. So I would say f of 2 is 3 times 2 plus 1, and that boils down to what, 7. Here I'm talking about g of 5, so I'm just simply letting x take on the value 5 here and performing an evaluation. So that would be what, 5 squared minus 1. So that's 25 minus 1 is 24. Okay? Alrighty. And we'll see in a little bit that these actually set up what we call functions here. For now, we'll just think of them as giving names to these various polynomials. Okay, a little more terminology we want to throw in here. The degree of a polynomial in a single variable, that's actually important here, because we will talk about polynomials in multiple variables later. Anyways, the degree of a polynomial in a single variable is the highest power of the variable that appears in any of the terms. Okay? Alrighty, so let's come over here. Suppose I have h of x is 17x cubed plus 4x squared minus 7x plus 1. That's a polynomial function, as you can see. This would actually have what? Degree 3, because 3 here is the highest power of x that appears in any of these terms, right? How about this one? I have k of x is negative 13x plus 7. Now, no power is actually written on x, but if I wanted to, I could actually, what? Write a first power on there. That would be, what? An explicit form. It's actually negative 13x to the first power plus 1. The highest power of x that appears would be, what? Degree 1. Now, usually we don't write the first power in there because taking x to the first power, no matter what the value of x is, you'll always just get x back, so it's kind of a waste of time here. But in a situation like this, you see the fact that there is a 1 implicitly there becomes important when we're attempting to assign a degree to k of x. Okay? How about j of x? Okay? J of x in this case is just 5. Okay? So the polynomial is just 5. Okay? It has no other terms other than that constant term 5. That actually has degree 0, and we'll see why here. You remember that x to the 0 is always equal to 1. Some people would argue, well, at least if x is not equal to 0. So here's what we're going to say here. We're going to think of 5 as simply what? 5 times 1, only in place of 1, we're going to think of x to the 0. So now I've written it in terms of x, and we can see that that ends up being what? 5x to the 0. The highest power of x that appears is what? 0. So it has degree 0. Okay? So that constant term has degree 0. That constant polynomial has degree 0. Okay, let's, as promised here, talk just a little bit more about functions. A function is a relation between two sets of objects. Okay, now when I say a relation, I want you to think of it like a machine here. This is one convenient way of thinking of a function. Okay, so it's a machine, okay, such that every acceptable input yields precisely one output. Okay, so if I have an acceptable input, okay, then I get one output and only one output. If you get more than one output, then it's something other than a function. Okay, now polynomials can be regarded as functions from the real numbers into the real numbers by evaluation. For example, suppose I have this function called k of x, which is negative 13x plus 7. Okay, I can think of this as a function from the reals into the reals, or the real numbers into the real numbers, in the following way. See, x falls into the machine, okay, k of x, and what spits out? Negative 13x plus 7. So k of x takes whatever you put into it, multiplies it by negative 13, and then adds 7 to that result. So if I was to drop 2 in there, okay, it would go negative 13 times 2, which is negative 26, plus 7 is negative 19. So negative 19 would pop out of the machine. Okay? Now you see I could drop any real number, any real number at all into that machine, k of x, and a number is going to come out, right? A different number, in fact, is going to come out. So we think of that as a function, okay? Okay? Only one output, though, okay? If it puts out more than one thing, then it's not going to be a function. Again, don't worry about this too much right now because we're going to be going through functions in depth in the next chapter. Okay? A polynomial of degree 2, by the way, is called a quadratic polynomial. You probably know this already. Okay? Such a polynomial yields a polynomial function of the following form. Y equals f of x is ax squared plus bx plus c. Now we've got to have a being non-zero. Okay? If a is non-zero, then this term ax squared would always be 0 and completely disappear. Okay? So we actually need that square term to appear, otherwise it really wouldn't be a quadratic function. Okay, so that means the leading coefficient, which I'm calling a in this case, is non-zero. Now I want to stop just real quickly for a second here. If I was using my original scheme for labeling coefficients, right? Remember this up here? Okay, I would probably label this what? A sub 2 x squared plus a sub 1 times x plus a naught. Okay? Now, that's kind of pedantic in a case like this. Let's talk about why we actually did this up here. You notice up here in the most general polynomial, the degree of that polynomial could be arbitrarily high, right? Maybe this is a 1,000,000 degree polynomial, right? So in other words, n could be 1,000,000, right? You can't just say a, b, c for what? For the coefficients on a 1,000,000 degree polynomial, because there's only 26 letters of the alphabet, okay? So in an expression in which the degree is open, like I've got here, maybe anything, what you're going to need is some sort of scheme to label the coefficients, okay, in a way that makes sense, okay? And what we did was what? Use a's with a subscript corresponding to the power of x. Very cool, right? Now we can talk about a polynomial of any degree this way. But in this case where you're talking about a quadratic polynomial, you know the degree is only what? 2, right? So that means you're going to have what? At most 3 terms, right? The x squared term, the x term, and the constant term. You might as well call those a, b, c, okay? So this is what's typically done here. So this makes it a little shorter and simpler, okay? Alrighty? Now, let's talk about graphing this thing. You notice that I put a y out here. I said y equals f of x. That's because we're going to imagine plotting points x comma y in the Cartesian plane, and then, in other words, graphing the polynomial function, I should say. Okay? All right? The complete graph of a quadratic polynomial function from the real numbers into the real numbers is called a parabola. Okay? So the name of the graph is a parabola. Okay? Alrighty? You probably heard of stuff like this, parabolic or paraboloid and stuff like this. Okay? These come from the word parabola. Now, the leading coefficient I'm calling a, right? I'm just going to mention a couple facts here. We can talk about proving them later, but I'm just going to tell you what the truth is now. If a is positive, in other words, greater than 0, then the parabola opens upward like this, okay? When you a parabola always ends up looking like either a smile or a frown, okay? All right, it's an infinite smile or an infinite frown. Goes on forever here. But if a, the leading coefficient, is positive, then it is a smile. It opens upwards. Think about this. Positive people smile, right? Positive leading coefficient, it's smiling. Okay, positive people smile. But if the leading coefficient is negative, then it opens downwards. In other words, it looks like it's frowning. Remember, negative people frown. Okay, so this is frowning. Alrighty? Now let's look at some graphs from Desmos. Okay, that's just a little free program, graphing program online that we can use here. And I highly suggest that you do use that. I'll probably do a video on that later on and show you guys the wonders and benefits of Desmos here. Here I've taken a couple parabolas, okay, a couple quadratic functions, let's say, and I've graphed them to get the parabolas here. Now let's look at the red one here. I've got y equals negative x squared plus 2x plus 4. Desmos went ahead and graphed that for me. You notice that what? The leading coefficient is negative 1, so it's frowning, as you can see here. It's frowning. Okay, and then I've got one with a positive leading coefficient. Y equals 2x squared minus 4x plus 1. Notice that it's smiling here, okay? It's opening upwards, okay? Just a demonstration of this thing that I mentioned before, okay? So that's always going to happen like that. All right, let's talk about a certain special point on any parabola, okay? We call that special point the vertex. Okay, every parabola, y equals ax squared plus bx plus c, reminding you here a is not 0, has a y minimum point if a is greater than 0, or a y maximum point if a is less than 0. In either case, this special point of the parabola is called the vertex of the parabola. Okay? The vertex usually has coordinates designated in the abstract as HK. I don't know where that came from, but people started using that in recent decades. So the x-coordinate of the vertex is H, and the y-coordinate is called K in the abstract here. Okay, let's show what I mean up here. Let's come back up here on this one. Okay, let's talk about the red one first. Notice that it is what? It is frowning, right? Okay, it's frowning. Notice that it has what? A high point, or a high point with respect to y, right? In the vertical direction. Okay, with the y values here. Okay, you remember when you're graphing, you've got the y's here, right? And then you've got the x-axis here. The vertical axis is the y-axis, and the horizontal axis is the x-axis. Okay, you see you've got a y maximum point here. Okay, all right, that is called the vertex. So in this particular case, for this parabola right there, the vertex is what? 1, 5. For this second parabola here, y equals 2x squared minus 4x plus 1, that's opening upwards. It actually has what? A vertex there, which is at what? 1, negative 1, and that's what? A minimum. That's a minimum point, a y minimum point. Okay? Notice that all the values of y that you could possibly get on this parabola are going to be what? Greater than or equal to 1. Negative 1, I'm sorry. And what? Up here in the red one, okay? Every y value you find for every point on that parabola is always going to be less than or equal to 5, because that's what? A maximum point for a y maximum point for that parabola. Okay? So just demonstrating that. Okay, so this always occurs in any parabola. You've got a higher low point depending on whether it's opening upwards or downwards. Okay? And I just stated what the fact we just noticed in the parabola y equals negative x squared plus 2x plus 4. Remember, the vertex was at 1, 5. So we would say that what? Our h is 1 and k is 5, right? With respect to that designation. In the parabola y equals 2x squared minus 4x plus 1, we found the vertex was what? 1, negative 1, just by inspection. So that h is 1 and k is negative 1, okay, in those particular cases. All right, let's keep going. Here's what we're going to wonder about. Suppose I'm just given the equation of of the parabola here, of the quadratic function. Okay? Can I figure out what the vertex is without graphing it? Okay? This is what we're going to do next. Okay? And I'm going to show you there is indeed a technique that we can use for finding the vertex. And that technique is called, I hope you can read this, completing the square. Okay? Finding the vertex by completing the square. Okay, now before I do that, let's talk about this. I claim, or we claim, that every parabola of the form y equals f of x equals ax squared plus bx plus c, again a is not 0, can be rewritten as the following: y equals f of x, a, that corresponds exactly to that a up there, a times the quantity x minus h squared plus k, where h and k is actually ends up being the vertex, okay? And I'm going to show you how to do this. Now, I'm not going to prove right now. Okay, let's say I was capable of rewriting this quadratic function this way, which you always can. Okay? My question will be later, how am I justifying and knowing that value right there is actually what? H, that is the x-coordinate of the vertex, and then the k over here is actually the y-coordinate of the vertex. How do I know that? I'm not going to address that question right now. Okay? Yeah, I'm just going to have you guys take that on faith. I will address that question in the next video. Okay? I'm just stating what the facts are. Okay? And I'm going to show you a technique for doing this right now called completing the square. Okay? But I claim if you do this, you can actually read the h and the k right off, okay, so that you'll have the vertex. Okay? Here's where I mentioned that we're going to demonstrate that technique first for rewriting it. Okay? Now, what I'm going to do is use this technique on the very two parabolas that we already graphed, so that way we know we're right. Okay? All right. Here's what we're going to do, and I'm going to go through the steps here. Now, when it comes to the exam, I'm going to ask you guys a question along these lines. So you want to be able to do this, okay? All right. Let's go ahead. Rewrite y equals f of x equals negative x squared plus 2x plus 4 in the form y equals a times x minus h squared plus k. And then use it to find the coordinates of the vertex, okay? So here's what we're going to do, okay? I just rewrote the original, so that's just starting with the original. Didn't even do anything yet. Okay, I'm going to tell you the steps to follow. Factor out the leading coefficient, okay? Okay, maybe while we're at it here, can you remember we were writing these as ax squared plus bx plus c? Can you tell me what a is? A would be -1, right? That's the coefficient on x squared. B would be 2, right? And c would be 4, okay? So those are the coefficients. Those are just numbers, okay? All right. Now, you want to factor out a from the x squared and x terms only, by the way. Do not factor it out from the 4. Just leave the constant term hanging out there. Okay? Now, a is -1, so I'm going to factor out -1 from the first and second terms, okay? All right? I'm going to factor out the negative from x squared, negative x squared, and I would have what? X squared in parentheses. I'm going to divide -1 into what? 2x, and I would get negative 2x here also, okay? So I factored, there's my a. Now, I could actually write this, you could actually do this if you wanted. I don't really recommend this, but I'll throw this in. I could actually write that as a -1 times the quantity x squared minus 2x. Now, here, quickly, notice that what? The sign or signature on x has changed from what? +2 to -2 because I factored out -1. Okay? Now make sure you did this part right, otherwise you're going to mess everything else up. Do a quick mental double check and multiply through using the distributive property on both these terms and make sure you get your original. -1 times x squared is negative x squared. -1 times -2x is plus 2x. And then we carry through the 4. We got it. Okay? Alrighty. Next step. Now you're going to have a coefficient on x in here. Okay? Okay? If it's 0, then you don't have anything to do. Okay? That's not generally going to happen here. Now, here's what you want to do. Compute the following. Here's the steps. You want to take half the coefficient on x and then square the result. Okay? Just the coefficient. That's the number. Okay, what's the coefficient on x up here? The coefficient on x up here in parentheses, I'm not talking about the original, I'm talking about in parentheses now. The coefficient on x is -2, as you can see. Now take half of that. That means divide it by 2, right? Taking half of something. So I go -2 and then divide it by 2, and I get -1. And then it said square that result, okay? So I square that result. I go -1 quantity squared, and I get 1. Don't forget your parentheses around here. If you go -1 and squared, that's -1 squared by PEMDAS. Remember PEMDAS? The order of operations, you square first, and then you would negate. Okay? So don't forget your parentheses here if you've got a negative number. Okay, so it's -1 squared is 1. Now, that's a magic number. I'm going to do what with it? I'm going to show you. It might look kind of kooky, but you're going to see it's going to work out here. Okay? I'm not sure I actually spelled that right. I put a D in there. Okay? Inside the parentheses, add and subtract this value that you found just above. In other words, the 1. So what I'm going to do is come back in here. See this expression I've got right here. And I'm going to first add. Always make sure you add first. And I'm going to subtract. Okay? You can see that adding the 1 and subtracting the 1 doesn't change anything, really, right? Because those would cancel out. So I really haven't changed my function. Okay? But I'm going to show you. Remember, I'm just rewriting things. I'm going to show you some tricks we're going to play here. Okay? My next step is to move the last term inside the parentheses outside the parentheses. Okay? I don't know how I got a D in these parentheses. Anyways. See that last term, the -1? I'm going to move it outside the parentheses. Now, don't forget your basic mathematics. Remember, everything inside the parentheses is being multiplied by what? -1. Okay? So when I move that -1 outside the parentheses, I'm actually what? Moving -1 times -1 outside the parentheses. So I actually get what? +1 outside the parentheses, because -1 times -1 is +1. Okay? You see, I've designated that here. You got to get that right. When students make an error, it's often right here at this stage, number 4, where the error occurs. Okay? Don't forget to get the right signature and the right value popping out. You can't just take the value and throw it outside the parentheses if everything inside the parentheses is being multiplied by something. Okay? All right, so keep that in mind. Okay, now we're essentially done here. Because if you've done everything right, what should happen? The thing inside the parentheses should be a perfect square, so you should just observe what it is the square of. Don't forget to carry through your negative. That's actually x minus 1 squared, if you think about it. Okay? Okay, if you take x minus 1 and square it, you will indeed get x squared minus 2x plus 1. Combine the like terms here, the 1 and the 4, to get 5. And now, notice that if you want to, you can put the 1 there. A is -1, as we stated, all the way back with the original. A is -1. Okay? But we've got what? Y equals A, x minus h squared plus k, right? Remember? Now, A is -1, so check. We had that. What would my h be? Well, don't forget in my formula, it's x minus h. So the x minus h would correspond to x minus 1. So h is actually +1. Okay? Don't get the signature wrong. Here's where students sometimes make a mistake also. And then it's plus k. So what would k be here? K would be 5. Okay, so k is 5. So h is 1, k is 5. So we've got a vertex of 1, 5. Aha! Isn't that exactly what we had from our graph? Yeah, if you go back and look at this, let's come all the way back here. we have, this is the one that's frowning, negative x squared plus 2x plus 4. And we had what? A vertex of 1, 5. Okay? It works. Okay? At least in this case. And again, I'm going to show you the details of why it works. I'm showing you the technique now. I'll show you why it works in the next video. I don't want to make this video too long here. Okay? Now I'm going to do the next one, the second parabola, and I'm going to do it more quickly here. I'm not going to write out each step individually, going 1, 2, 3, 4, 5, 6. We're going to compactify this just a little bit. Okay, y equals 2x squared minus 4x plus 1 by completing the square. That technique I just used was sometimes called completing the square. Okay, I completed the square inside the parentheses up here is what I did. Okay, once we did that, I completed the square in there. Okay, let's do it though. Okay, here's my original. Y equals 2x squared minus 4x plus 1. Factor out the 2, right, the leading coefficient, from what? Just the first two terms, just the x squared terms and the x term if you're writing in descending order, which you should be. Okay, factor out the 2, and I've got in parentheses x squared minus 2x in parentheses and plus the 1 hanging out there. Okay, now I just did this mentally here. I see that's supposed to be a little thought cloud. Okay, I take the coefficient on x inside the parentheses, which is negative 2, divide that by 2, right, cut it in half, and then square the result. And I get 1 again, just like I did in the previous problem. Okay, now what do I do here? I come up here and add that 1 and then subtract that 1 inside the parentheses. And I've done it right there, you see? And then what's my next step? I want to move that last term from inside the parentheses to outside the parentheses. So I take that negative 1 and move it outside, but that's not what I'm really doing. That negative 1 is being multiplied by what? The coefficient on the front, 2. So when I move that negative 1 out, I'm actually moving a negative 2 out, you see? Right there, okay? And then that's going to be added to the 1 on the outside there. So I've actually got 2x squared minus 2x plus 1 minus 2 plus 1. Okay, this thing in parentheses should be a perfect squared. Once again, it is x minus 1 squared. Okay, so we've got 2 times x minus 1 squared, and this is minus 1 when we combine these constant terms. So you can see once again that h would be 1, but k this time would be negative 1, and the vertex on this particular parabola should be 1, negative 1. And if you remember looking at the graph here, that's exactly what it was, 1, negative 1. Okay, well, I hope you understood that. We shall continue in the next video.